So I'll go through the Megacities Carbon Project itself. I'll talk about the motivation for it, the methods we're using, some examples of the types of measurements we apply, both from the ground, air, and space. And I'll give some examples of what we're seeing in Los Angeles. I'll stop shy of giving results because we're not that far along yet. But then I also, since I have the podium, I want to talk a little bit about emerging science and policy challenges in this domain. And I'll leverage off of the Megacities project to do that. That latter topic is informed somewhat by another project that I lead called NASA's Understanding User Needs Project. This is part of a program called the Carbon Monitoring System Program. It's a congressionally mandated program to improve the utility of carbon data sets, and it uses a number of ongoing collaborations with different agencies, including the California Air Resources Board. Now, I don't know how to back up unless I use it. Maybe let me try the red arrow. So the problem with using these methods I'm talking about is they're big data, and that means bogging down presentation computers. So this is supposed to be an animation, but use your imagination. Why do we focus on cities? This may be used from the University of Duh, but most of the fossil fuel CO2 emissions are concentrated where the people are, and most of the people today live in cities, and this is increasing. Urbanization is increasing. It's predicted to double between 2010 and 2035. So there it's going. And what this shows is an atmospheric simulation showing emissions of carbon dioxide. And if you watch, you'll see puffs being emitted from all the major urban areas and the power plants that feed those urban areas. In fact, in 2010, the 50 largest cities collectively generated enough fossil fuel CO2 to make them the third largest emitter behind China and the U.S. And there's some double bookkeeping there because some of the largest cities are there, but you get the idea. And to be a little bit more specific, if you're trying to look at most of the emissions, and that's what this bottom figure on the right shows. Let's say you wanted to look at 99% of the fossil fuel CO2 emissions in the U.S. You'd have to look at a map that looks like the bottom right-hand figure. You'd have to cover about 33% of the land. But if you could be satisfied with only getting 80% of the net emissions, then you'd only have to look at the top figure, only about 3% of the land. I'm just pointing out the fact that we have scientists call this log normal behavior. The emissions are concentrated in small areas, and if you can focus your resources, both from a policy sense and from a scientific sense, you can get a lot of bang for your buck if you can be satisfied with less than perfect coverage. So that's kind of the idea there. The other reason why we focus on cities is the most rapid change in fossil fuel CO2 emissions is happening in cities, both in terms of growth and stabilization. These are two cities in China, Beijing and Tianjin, megacities, and look at that stupendous growth in emissions over the last decade or so, and that's only going to continue. But at the same time, cities are kind of serving as first responders, along with the state of California, for climate change. Groups like the Climate 40 Group, the Compacted Mayors, are making significant commitments to stabilize emissions at urban scale. They're not waiting on the UNFCCC. They're doing this. They're moving forward. And also in California, we're familiar with carbon markets and the fact that there are pilot markets arising around the world at subnational scales. In this case, the figure on the bottom right shows 5 carbon trading systems in 5 Chinese megacities and 2 provinces. So this is happening in parallel with what's happening at the nation-state level. Why do we need to measure urban carbon? Well, Mark and others pointed out the fact that we're doing a pretty good job with inventories at larger scales, the scale of countries and states. But when it comes to estimating emissions of cities, individual cities, we either have no data in many cases or there are large uncertainties. And that's true for CO2. Carbon dioxide, even though we have 10% uncertainty, say at the state level in California, in many cases it's 100% uncertainty at the level of individual cities, even though we have new accounting protocols. The data collection systems just aren't there yet. And it's even worse for methane. As Mark highlighted, methane is largely uncertain at all scales, and cities are no different. The good news is there have been recent advances. Mark nicely summarized the approach of top-down methods and improved bottom-up estimation methods, so I don't have to cover that. What I'm going to talk about is this pilot project called the Megacities Carbon Project. Megacities plural, meaning it's not just Los Angeles. In the current phase, we have strong partnerships with both Paris and Sao Paulo, and we're working together to answer these types of questions. What are the carbon emissions of cities, and how are they changing? More importantly for us, why are they changing? What are the specific sectors, policies, and behaviors that are responsible for changes, whether it's growth or stabilization? Are mitigation efforts having the intended effect? Again, plural mitigation efforts, because most cities are implementing a portfolio of responses to climate change, not just one. And how accurate is the urban carbon data? If we're going to be doing emissions trading, do we trust it? And finally, very important, can we share data, carbon data, transparently between cities? A lot of what I'm talking about is organic. It's happening at subnational scale. Well, if we can set up data sharing, that's something that the countries haven't been able to do as easily yet. We picked Los Angeles because it's a big city. It dominates the urban emissions of California, and it is unique in a number of ways, including sectors we'll talk about at the end. So how do we do this? Methods. The first thing that we do, and Mark talked a little bit about this with methane in California. I'm going to talk about it here with fossil fuel carbon dioxide. We start by generating our best possible estimate of fine-scale emissions data with functional information. What I'm showing on the top figure here is what we call Hestia. It's a data product in Los Angeles that takes data on building classification at the parcel level, sometimes at the building level, building age, building type. We do have energy statistics such as gas use, and we can produce block-level emissions estimates. We can do the same thing with the transportation sector, the on-road sector, which frankly dominates the emissions in Los Angeles. So what we have in this type of product is very rich space-time sectoral information on the key drivers for emissions. Now, how do we combine this with the atmospheric measurements that Mark talked about? What I'm showing you here are two things running at the same time. This is about a 3-day period going back to fall of 2011. The figure on the left is that initial estimate of emissions that I talked about, at hourly resolution, about 1 kilometer. What you're seeing here is the breathing of the LA megacity. The things that are pulsing and changing over time are the freeways, right? You're seeing the diurnal patterns of the freeways, right? It's like one big system. You're seeing urban metabolism. The persistent red spots are the persistent large point sources like power plants. The right is if we take those emissions and we now propagate them into concentration space. What does the CO2 look like in the atmosphere as it's moved around by winds and the day-night motion of the atmosphere up and down? This is why Mark said you need an atmospheric transport model to make sense of any measurements that you make in the atmosphere over here on the right and to translate them back to what the emissions are, right? So whether you're going forward in time and trying to test your predictions of what the emissions should manifest in the atmosphere, or whether you're trying to measure the concentrations of gases on the right and invert to get the emissions. This is the back and forth that we do with this thing. Okay, so to make these measurements in LA, Mark mentioned a statewide network. We have a subset of that in Los Angeles. We now have 15 sites. 14 are online. Those are the green pins. The yellow one in Ontario should come online later this week, fingers crossed. And these are pretty complicated, and I don't have time to get into this, catch me at the break, but it's hard to get sites in a place like Los Angeles because of the geographical reasons, because of zoning reasons, a lot of other hard reasons. There's a reason why we don't just have these everywhere. But we have them on everything ranging from radio towers to tops of mountains to buildings, and those introduce measurement challenges when you're trying to make the precision and accuracy Mark talked about, the devil's in the details. But I just want to highlight that it's important. We don't just put them where we can get access. We put them in strategic places around the city because there's a lot of variability in carbon dioxide. I'm just going to show carbon dioxide here and the other gases across the city. The upper left-hand figure shows you the average diurnal or day-night changes in concentrations of CO2 by season. Those are the different colors. And by time of day. That's the horizontal axis. So you see this variation, very large variation over time of day in what you measure in, say, Compton, which is very urban, versus, say, Palos Verdes, which is on the coastline, versus San Clemente, which is on an island, which is just flat. It's a nice background site. So the point here is you have to have measurements that capture the things of interest, and it varies significantly over a city as complex as Los Angeles. Satellite observation. Satellites are developing the capability to see emissions, or to see the atmospheric footprints of carbon dioxide and other gases from space. This just shows us an artist concept of the different techniques in place. I actually had an animation, which I don't think will work. I think I replaced this with a static. No. Huzzah, it's working. So what I'm showing on the left is actually how the NASA's orbiting carbon observatory satellite samples cities when it flies over. Right? So OCO is designed to look at carbon dioxide around the world. But every once in a while, it flies over a city. And when it does, we can do what's called target mode. We can tell it to just basically rock back and forth as it goes over the city. So over the course of a few minutes, we get 10,000 or so measurements. And you can actually map out the CO2 concentrations over the city during that pass. Now, OCO wasn't designed to look at cities, but OCO 3, which should launch later this decade, we hope, We've added a city mode. So this thing does a raster scan. When it comes over a city, it maps across the city, about 100 kilometers on the site. So again, we get thousands of measurements. And OCO3 is set up so that we do this for all the world's cities, or all the large cities, every few weeks. So we try to get about 1,000 cities and about 1,000 power plants globally every few weeks. We're trying to go after them because, again, that's the big source of emissions. Meanwhile, we're not waiting on the next generation satellites. We're testing these remote sensing technologies in Los Angeles. So we have an observatory on top of Mount Wilson that I call a faux satellite. It's a laboratory with an instrument that looks like a satellite you would put on a weather satellite, a geostationary satellite, and it just sits and stares, looks across the LA basin several times a day, looking at reflected sunlight. And like the satellites, by measuring the amount of absorption in different spectral bands, you can measure what the concentrations, of greenhouse gases there are. And it has the ability, because it can scan across space and time, it has the ability to go to the next slide. Sorry about this. Too much data. So it has the ability to map out patterns of different gases. The figure on the left just shows a map of methane to CO2 correlation ratios. The takeaway is it shows you where there's more or less methane, so there's a big blob of methane in the central part of the LA basin. This is persistent over about 2.5, 3 years. And on the right, we have some early maps that are doing the same thing with carbon monoxide and CO2. Now, Mark mentioned radioisotopes, and I just want to briefly mention that because I'm not going to talk about it here, but we're also measuring radioisotopes in LA, and together with the carbon monoxide measurements and CO2 measurements, we can get a sense of fossil fuel component. And that's important because even in a city like Los Angeles, it's not all fossil fuel. We've got a significant biosphere component. Our initial results are that we think about 20% of the CO2 we see in the air over LA is due to the biosphere, which shocked me because it looks like it's all covered by concrete when you fly in by the air. Scientists call it impervious surface. But there's still a significant biosphere in Southern California that matters. Right, not all fossil fuel CO2. Okay, so real quickly in the time I have left, I want to tee up some emerging challenges. And I would say that as a departure from what we've been talking about, which is using atmospheric measurements and other data sets to test the inventories. Some scientists have fun falsifying inventories. The question here is diagnostic. Getting away from, or can we account for methane in particular? Can we help directly influence mitigation? And let me give you an analogy. If you have leaks in your sprinkler system in your yard, if you still have a sprinkler system, and I encourage you to get rid of them, go native. But if you still have a sprinkler system and you know you have a leak because of your water bill, you don't need to measure your leak rate to high accuracy, right? You know it's leaking. But finding the leak without digging up your whole yard can be challenging. If your yard is the size of a state, you can do a lot of digging. So the idea here is find big leaks. It's called threshold detection. So what I'm showing you here is the technique we're testing now in the Central Valley. I have a poster session on it. I have a poster talk on it this afternoon. But the idea is to use satellites to identify hotspot areas where we have a lot of methane, or using the techniques Mark has talked about in the Central Valley. We then use aircraft that can fly over methane sources and see the invisible plumes and just say, plume, 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 leak, leak, leak. It's like finding the wet spots in your yard where your sprinkler's leaking. And then we follow up with cars, right, to confirm it, right? With limited resources, we focus on where to send the cars. And in the Central Valley, this is in Kern County and Tulare County, just an example. So far, based on a few days of flights with NASA aircraft, we found about 200 major emitters, point sources, both in the oil sector and the dairy sector. But that's out of tens of thousands. So it's not all of them, right? A lot of the research that we're seeing shows that a fairly small number of emitters are responsible for most of the emissions. And that's important because it means you can focus your resources on helping people find their leaks and fix them. If I look at this for LA, we've done the same thing. The top figure is an example from an oil field. Those green plumes you see are invisible plumes of gas that the aircraft has imaged. And the bottom right-hand figure is from a landfill. You can see plume coming out of that's actually Flint Hill landfill. It's the biggest landfill in the U.S., or was. It's now being shut down and covered. Two other big picture things. One is assessing progress. And so again, separate from testing inventories, California has a very ambitious program to reduce its greenhouse gas emissions, and that's great. But the question is, let's say it's 2020, we're trying to assess whether we're going up or going down, or we're bending the curve enough. I would assert that some of the things the science community needs to do is to do a better job at quick assessments, not 5, 10 years late, but now, and even better, short-term projections. Can I do a 1 or 2 year horizon projection to say, is the state rolling off that curve at 2020? And if not, why? So it's the latency and overshoot challenge that we're trying to grapple with now. The last thing I'll point out, and I started with this, is it's not enough just to say we think the inventories are wrong, and we think that we're underreporting and we need to make some adjustments. We need to understand these processes. We understand the carbon cycle urban scale. And this is something that gets beyond making measurements in the atmosphere. Urban systems are complex systems. They have the built system, which is what we as humans build and spew stuff into the air from. It's urban ecosystems. It's urban aquatic systems for most cities. Most cities happen to be on water bodies. And then it's all the drivers, the socioeconomic drivers and geographical drivers. This is what I meant at the start of this talk by saying it's not something that a single discipline can address. It truly is multidisciplinary, and this is something we've written about with some of our colleagues in the social sciences and engineering. Hopefully last slide. So, and cities are important because they're the biggest emitters and they're changing quickly, and they're also some of the first rapid responders to climate change. We still have big gaps in the data, but we have advances in technology that can help us fill those gaps. And the nice thing about pilot projects like the ones I'm talking about is it offers us the opportunity to collectively build capacity, technical capacity, in other cities around the world and do data sharing. And I guess last thing, like I said, I have a poster this evening on San Joaquin Valley methane emissions, and please follow us on our website. Thanks.